Hello, and this is lecture 5 in our Maps, Images and Structure class, and today we're going to be dealing with faults. So let's remember what it is we've learned up to this point. I hope by now you remember that outcrop patterns are caused by the intersection between geology and topography, where the structure contours are cutting the topographic contours. We also learned that dipping strata have parallel structure contours with a consistent spacing if it's a continuous regular dip. We learned that there were different sets of structure contour above and below unconformities. Those are completely independent of one another. And we also learned that igneous intrusions cut and are therefore younger. They postdate the stratigraphy into which they are emplaced. We learned that folds result in complexities in the structure contour. In a folded sequence, the structure contours are not regular or parallel. And we learned that structure contours can be used to describe 3D structures on 2D maps. So looking at the 2D map, you can then draw a cross-section and understand geological structures in 3 dimensions. So what is a fault anyway? Well, a fault is a brittle fracture in the rock, and it's not enough for it just to be cracked. It has to have moved along the crack. And you can see in this nice example here where we have a sharp juxtaposition of different rock types against one another. The light coloured rock, for example, has been dropped down here and a little bit again there. So although faults are really in reality not two-dimensional, we often treat them as so on geological maps. We think of them just as simple planes, even though faults usually have a thickness of deformed fault rock within the juxtaposition of the fault plane. So essentially a fault plane, just like other geological surfaces, can be described by structure contours, and we can use the differences in the structure contour across the fault to look at the amount of displacement, which is something we often want to do. In reality, faults often curve and they branch, and eventually, of course, they die out. No fault goes on forever, although in our worked examples, essentially that's not going to be an issue. And so when we're describing a fault, just like a bed, we're interested in the strike and the dip, and we can use this to help us understand how much displacement has occurred across the fault. So in this particular example here, you can see this is the fault surface dipping down towards the right, and this pink coloured dike here has been displaced across the fault surface. It's essentially a marker. So you can see that it's been dropped down this much, and we call that the throw. It's also been offset horizontally, and that is what we call the heave. Furthermore, we refer to rocks on either side of a fault. The blocks on top of the fault plane are referred to as the hanging wall, and the footwall is on the other side, and this comes from a mining term. You could imagine if you were going down a tunnel along the fault plane, the footwall would be at your feet, and the hanging wall is where you hang your miner's lantern. So it comes from a mining past, and people often refer to hanging wall and footwall. It's important to know that. So there are 3 different types of fault, and we're going to be looking at these today. The first is a normal fault. A normal fault is one which just involves vertical displacement and extensional displacement. So in this case, the motion of the hanging wall block is down relative to the footwall block. The motion is down in the direction in which the fault dips. And a reverse fault does exactly the opposite. The hanging wall block is uplifted and it moves only vertically, and then sort of, yes, up the plane of the fault. So they are precisely the opposite of a normal fault. It is worth noting that a lot of reverse faults are actually quite low angle. This one you see is quite high angle, and you do find high angle reverse faults, but a lot of them are low angle, and when they do that, then where they're often referred to as thrust faults. And last but not least, these are called dip slip faults, and then the contrast to that is a strike slip fault. On a strike slip fault, the two blocks move only horizontally relative to one another. Because in reality, we often get a mixture of reverse and strike slip, or strike slip and normal faulting. Usually faults don't only move in one perfect direction, although there's usually a dominant sense of motion. So in the case of strike slip faults, we describe these as they can move in one or two directions, right? So either the block here on the top moves to the left, or it can move to the right relative to the other block. And we use this to name this type of faulting. So if it moves left, we call it a sinistral fault, after the Latin sinister for left, and dextral is, of course, dexter, right in Latin, moves in the opposite direction. And so it just, if you can easily imagine, it doesn't matter which block you're observing here. Imagine yourself standing on this lower block, and this piece here is moving to your right, so that means it's a dextral fault. So once you've identified what sort of a fault it is, you can also, just like we did with the folds, it says something about the strain and stresses in the rock, right? The sort of stresses that have caused the faulting in the first place. So in a normal fault, which is an extensional fault, this means that the weakest, the lowest sigma 3, is perpendicular to the fault, is essentially horizontal. So this is essentially like an extensional rather than a compressional feature. In the normal fault, the vertical axis here, that's the sigma 1, the greatest stress. Compressional stress is horizontally, essentially pushing down the hanging wall block. And sort of like pretty much the opposite here in the reverse fault. In the reverse fault, this is a compressional feature like a fold. So sigma 1 is horizontal here, and sigma 3 is vertical, which is one of the reasons that the block is able to rise up along its fault plane in a vertical fashion, because this is weak and the horizontal motion is strong. And last but not least, we've got our strike slip fault, and in this case the sigma 1 is parallel to the fault itself. You can imagine that's the strongest compression, so it's pushing this block, in this case the hanging wall block, is being pushed along to the right side of this diagram. So let's think a little bit about how you would see a fault on the map. It's not terribly complicated. There are easy ways of spotting faults on maps. One of them is, just as we've seen in some of these earlier cartoons, there is a displacement. There's a break in the strata and an offset here. This orange unit, for example, is lower on the right side and higher on the left side here. This is indicative of fault. This middle example is slightly trickier. What we're seeing though here is a repetition of the stratigraphy. The pink, orange, buff color is repeated across the fault. Normally you wouldn't see that. Usually you just go up and down the stratigraphy. You don't see a repeat. So that's also an indication that you have a fault in here, probably a thrust fault. And last but not least, we see a dramatic change in stratigraphy here between the well-bedded units on the left here and something really crazy and folded here, and this sharp change in the geology essentially requires us to put in a fault here to explain it, because you can't offset these against one another. It doesn't make any sense. So when we're trying to understand how faults have moved, we can understand this on the map, and I'll show you now how to do that. So the first thing is to figure out which way the strata on either side of the fault are moving, and we do that using our old friend the rule of V's, or structure contours, to decide which way the beds are dipping. And then we have to figure out which is the downthrown side, which one has the younger rocks in it, right? And the trick here is that normal faults have younger rocks on the downthrown side, and the motion is towards the downthrown side, whereas normal faults is the opposite. The direction of motion is away from the downthrown side. It's going up. And you can see this a little bit here, where we get, there's a fault here which is dipping towards the right of the picture, and this is mostly a normal fault. It's entirely a normal fault. It's dropping down this section, and you can see the offset of the orange rock across this. Now it's interesting to note that it appears to be displaced horizontally, but that's not really true. This is completely a vertical motion. So yes, we can use structure contours to image and measure the amount of motion across a fault. So for example, in this case, you can see there is a 400 red contour here for this boundary here, the blue to green, but we have a different value on the other side here. So it is important to remember that the structure contours are different on either side of the fault, right? So here we have the 300 contour here, but it's actually only 200 on the other side of the fault. You can't these happen to match up, which is very nice, makes life easier, but you have to recognize the fact that this is a different value. As soon as you cross a fault, you're going to get a different value to your structure contour, and that will allow you to determine how much motion there has been on the fault. In this case, about 100 meters, exactly 100 meters. So here's an example of a map that shows what appears to be horizontal displacement, but which isn't doing that at all. It's all vertical. So you can see on the top here we have 5 beds, each with their own interface, and we have structure contours showing in the different colors here the depths of those different contours. And here's the fault running along the middle of the map. The topographic contours you can see roughly parallel horizontal here. So on the other side of the map you can see here how the structure contours have different values. So this is orange 90 here, this is orange 100 here. So there is a down dropping of about 10 meters, or exactly 10 meters, along this line here of that interface, but no horizontal motion. So the values are different, but you can see the structure contours still align like that. So if we then pick out the contours in the way we do, where they intersect the topography, we can draw in the boundaries of these faults and color that in. And so what you end up with is something that looks like that. So this you might think here, this is a strike slip motion because there's horizontal displacement, but this is just essentially an optical illusion. The beds are just moving vertically relative to one another, and the effect is given because of the dip of the units towards the top right of the diagram, and because of the slope in the topography. So you have to be a little bit careful about that. Here's some real examples of this. So these are 2 examples from the UK where there appears to be horizontal offset. There is horizontal offset in the map, but in reality these faults are actually completely just extensional normal faults. There's no strike slip motion going on. It's purely a function of the topography and the dipping of the beds. One other feature you often see in geological maps is the repetition of strata, and this shows you how that works. If we had the pink, orange, light orange beds here on one side of the fault with a steep dipping reverse fault here. So as this hanging wall block has moved up, it's moved vertically, but what's happened here, the outcrop on the flat outcrop here, you can see there's a repetition of orange, pink, and that's essentially a dead giveaway for the presence of a reverse fault. So you notice that we saw repeating patterns where there was folding, but that was a mirroring. This isn't a mirroring, this is just the same units. So we have ways to depict faults on maps, and you need to learn these symbols. They're very common, internationally used. So essentially for a regular fault, it's usually a normal fault. Essentially we have a solid line and a little tick on the downthrown side, and then usually next to it there is a degree value, which is the dip of the fault plane. And typically normal faults are depicted in this fashion. With a thrust fault, you have these little teeth, these triangles here, and they're always on the upthrown side. So this shows you that this block is moving up. It's the hanging wall block, and it's moving up relative to the footwall block over here. And finally, strike-slip faults, and usually we depict these with arrows showing the sense of motion. So, as usual, we want to try and use our map data to try and understand how things work in 3 dimensions, and in particular to draw a cross-section. So, what we do when you're drawing a cross-section is you follow the rules you've been using up to this point, and essentially where the section crosses the fault, we mark in this fault. It is important to remember the apparent dip problem. So if your fault was dipping at 80 degrees, you would only mark it in as 80 degrees if it was cutting the fault perpendicular. Otherwise, you're going to have to recalculate that, and you calculate the apparent dip depending on how oblique the section is cutting the fault. If you don't have any information about dips, then usually you just draw them in vertically, but usually we know better than that. So one of the crucial things about faults on cross sections is that whatever the stratigraphy is like on one side is usually as it is on the other. What I mean by that is that the thickness of the beds, say the orange bed here, is the same thickness on the right side of this cross-section as it is on the left, and all the other units as well. So this means that the dip on the beds also is the same on both sides of the fault. It's been offset, right? So this is the dip here of this pink unit, theta, but it's the same on both sides. It's just been moved relative to one another, but it hasn't bent it. And that allows us actually to put things back, so you can restore a faulted section to its pre-faulted state and try and understand how much motion there has been across the fault. And we can use, of course, the cross sections to estimate how much motion there's been, particularly throw. You'll remember that's the vertical distance, and again a little bit of simple geometry is what's required. It's not the same as the motion along the fault plane, it's the vertical motion, it's the throw. And we do that with a little bit of simple geometry. You know the dip on the fault, and you know the total amount of motion, so you can calculate the throw on the fault. Yeah, that's important. If you're also, it's important in this case to draw it oblique. Otherwise, you get an overestimate. And again, important, doing this only accounts for 2D motion, so we don't know anything about motion essentially in and out of the page. So, yeah, if you want to read more about how to look at faults on maps, you can use this QR code here. Essentially, what this often boils down to is looking at some feature that's on both sides of the fault, like a dike or something distinctive, which is then offset on the map. And we can use that to understand the sense of motion and the amount of motion, essentially features that have been offset by the faulting that you can then restore, particularly through drawing a cross-section. So last but not least, we're going to do a little practical here today, what you're going to do is draw structure contours. You're going to make a cross-section and the dreaded vertical stratigraphic scheme, and then I'd like you to write an interpretation. Okay, thank you.